Hello everyone, welcome back to one more question from inorganic chemistry. Here we are having a question which is one or more than one correct type of questions, the expertise of IIT-JEE Advanced. So here we are having a question about the compounds of boron and nitrogen in particular. So the four options given to us are number of sp3 hybrid carbon atoms in the borax are greater than 10. We need to know the structure of the borax for that, then only we can answer this particular question, this particular option. And then we have got the BN bond length of the following compounds. So these compounds which have been given to us, many of the students may not be very aware of what are these compounds. Borazine is actually that inorganic benzene B3N3H6. And inorganic graphite, as the name suggests, it can be some compound of the boron and nitrogen, which is having the bonds between boron and nitrogen, and which is going to have hexagonal structure, just like we are having in graphite. So actually this inorganic graphite and borazone, they are coming from the same thing, boron nitride. The difference is borazone is the cubic form of boron nitride, just like we used to have for the diamond, and the inorganic graphite is the hexagonal form of boron nitride, that is hexagonal boron nitride, which is having structure similar to graphite. That's how this name inorganic graphite and borazone is coming. Then we are having in solid orthoboric acid, 6 hydrogen atoms are associated per molecule. Again, we need to go back to the structure of this boric acid in solid form, how it looks like, then we can be able to see this answer. And the last question was maximum number of hydrogen atoms present in a plane of Diborane. That is very much famous question. If you have seen the structure of Diborane, you can easily comprehend what this thing is about. And if you see, finally we'll be coming to conclusion that the answer for this question was this option number A, answer option number C, and option number D. These were the correct options. So this option number B was only which was not correct. How that option we can rule out, we need to go a little deeper. We'll be talking about these options one by one. Here we go. The very first option about the structure of borax. So borax is the structure is over here, and actually the point of confusion is when the formula of the borax we have seen earlier in earlier discussions. You might have seen we used to add this is Na2B4O7.10H2O. So this is not the 10 water molecules which are completely present as water of crystallization. Only 8 water molecules are the water of crystallization. The remaining 2 water molecules are bonded with Na2B4O7. And the actual formula of the borax now we are supposing is we are realizing is this thing, B4O5OH4 and then 8H2O. Now if we try to draw that structure, the structure comes out to be like hexagonal ring kind of structure is there. So if you assume this hexagon, we can see there are alternately boron and oxygen present. This is how you can remember how to draw the structure of borax. So you are having alternate boron and oxygen atoms present, that is 6 atoms. Now out of this hexagon, 3 atoms, boron, oxygen, and boron are also the part of another hexagon. Like this is one oxygen, and because oxygen and boron are going to be alternate, this is another boron, another oxygen, and another boron. So this is kind of a chair form of the cyclohexane we have seen. This is a regular cyclohexane we have been drawing in 2-dimensional plane. Earlier we might have seen this kind of thing. Okay, so now we are going to see the boron, which are not because there are 4 water molecules present over there. Here we have seen 4 hydroxyl groups are present. So our compound is going to have 4 OH groups present, and these OH cannot be attached to oxygen. These OH must be attached to boron atom only. So knowing this thing, if we are realizing that we are having the boron which is having one OH also present, this boron will be forming 4 bond, that's going to be sp3 hybridized. So all the borons which are having 4 bonds, that is boron number 1, boron number 2, they are sp3 hybridized. This boron is sp2 hybridized. Okay, and then when we realize that this oxygen which is present over here, this can be undergoing back bonding with boron sympathy orbital. This oxygen can be undergoing the back bonding with the boron. So this oxygen's hybridization, this oxygen's hybridization will not be sp3. Those atoms are going to be sp2 hybridized. This is what we expect. Okay, and So the sp3 hybrid atoms we have labeled over here. This is oxygen in water molecule 100% sp3 hybridized. These two boron definitely sp3 hybridized. Now this oxygen which is bonded to sp3 hybridized, this oxygen atom cannot have back bonding possible. If there is no back bonding possible, this will remain in sp3 hybridization. Same situation is for this oxygen which is bonded to sp3 hybrid boron, and this oxygen also, this is flanked by two sp3 hybrid orbital, sp3 hybrid borons, so that is also going to be sp3. So the total number of oxygen atoms which are sp3 hybridized are going to be, this is your 8, 9, 10, 11 oxygen atoms are sp3 hybridized, and 2 of these boron atoms. So total 13 atoms we can see are present in the Boric structure, which are going to be sp3 hybridized. Remaining all atoms, all the borons and the oxygen atoms, we will believe are present in sp2 hybridized state. Okay, so that is the discussion. That is how we are deducing which atom is sp3, which atom is sp2. So the answer to the question that the total number of sp3 hybrid atoms in the borax are greater than 10, that is true. sp3 hybrid atoms, the number of sp3 hybrid atoms is more than 10, that is true, and this is actually equal to 13. Okay. Now, talking about inorganic graphite, the second option was talking about inorganic graphite, borazine, and borazone. So this is inorganic graphite. Structure is like graphite. So one hexagonal layer, as you can see here, this is one hexagonal layer, this is another hexagonal layer, and they are connected by the van der Waals forces between the layers. So this is the hexagon you can see, and there can be boron, nitrogen, alternating present. And we expect there will be some double bond that may be having some delocalization. We have not shown that for the sake of clarity. And when nitrogen will be sharing its electron with the boron, then this can be converting into sp2 hybridization in this particular case, because its structure is going to be like what we have seen the structure of carbon in graphite. So this is hexagonal form of boron nitride. We should have written it HBN, that is hexagonal thing. Cubic boron nitride we'll be writing for borazon, which should be written as CBN. So this is similar to graphite as we're talking about. Each nitrogen and boron, this is the structure which we can think of. So every alternate corner, boron, nitrogen is super present. We are trying to see this is how graphite looked like. Now, rather than graphite, carbon everywhere, we are having alternately boron, nitrogen present. So each nitrogen and boron will be now in sp2 hybridization, because all of these are forming 3 bonds. Although there will be some charge separation, positive and negative charges appearing. That is because boron and carbon both are forming the different positive and negative charges. So bond length of boron in this particular compound is found to be 145 picometers. That is actually the data which we may not be knowing already, but we can comprehend from the options which were given. Qualitatively we can tell. Quantitative values we may not able to remember. We are after all human beings. We are not supercomputers which can recall the data just at one click. Okay, so these bonds are relatively longer in comparison to borazole, which is supposed to be relatively actually both of these compounds are polar. Saying that they are non-polar, it's not valid. Both of these compounds can be polar. A difference in polarity can be there. So this is going to be a state where boron and nitrogen are bonded to the boron and nitrogen only. No other atom is coming into picture. Now going to the next molecule, which is borazine. This is sometimes we are also calling as borazole, or because of its structure similarity with the benzene, we are many times calling this compound as inorganic benzene. Here again, every carbon is going to be in sp2 hybridization. There's the structure. So all the atoms are forming 3 sigma bonds and 1 pi bond. Every atom is now having 1 hydrogen as well, and that's the point of difference from the structure what we have seen earlier in the inorganic graphite, because there was no hydrogen. Here we are having hydrogen also coming into picture. That gives us a little bit difference in the bond length. This is a relatively shorter bond. Because of that, BH bond and NH bond, they can also be having some polar nature, and that polar nature can be giving us some difference. So this time this bond is going to be a little bit shorter what we are seeing in comparison to it was in the graphite. And because we can expect a little bit more attractive forces, that positive and negative charges what can be present over here in comparison to graphite, this is supposed to be relatively a little bit shorter bond in the nitrogen and boron thing. And we compare this with the reactivity of the benzene. This compound is supposed to be relatively more reactive than benzene because this is relatively polar. So any nucleophile, any electrophile can find it easier to attack onto this in comparison to benzene, where there are no polar bonds. Although that there are electron-rich regions present, this is relatively much electron-richer. So here attack of the electrophiles or nucleophiles can be relatively more easily possible. That was Borazine. Going to Borazone. This is a graphite, this is a diamond kind of structure. We call this as cubic boron nitride. So if you see this is nitrogen atom we have tried to show, this is the boron atom we have tried to show. So everything is forming 4 bonds, implying that everything over here is going to be sp3 hybridized. If it is sp3 hybridized, its bond length is going to be highest. In our option which was given to us, we were told, this is actually how we can think about in 3-dimensional space how boron and nitrogen are going to be connected to. So every boron connects with the 4 nitrogen, every nitrogen connects with the 4 boron in 3-dimensional space throughout the molecule. Because it is sp3, this bond length is going to be relatively longer than both the earlier cases. That is the thing wherefrom we can conclude that B option was not going to be the correct, because Borazone, which was coming from the diamond-like structure, must have been sp3 overlap, and that would be giving you the longest bond in comparison to Borazone, or in comparison to Borazole, or in comparison to inorganic graphite. That was all about option number B. So the correct order of the bond length would have been that Borazole, that Borazole means we are talking about inorganic benzene, was having the smallest bond length, and then it was inorganic graphite. That would be the thing. And then the highest bond length was in this Borazone, which is the diamond, like analog of diamond. That was option number B, the correct order. Then we have option number C, where boric acid is having planar structure. So this is the structure which we are showing over here. This is one boric acid molecule, and then there are other boric acid molecules which are connected. So boric acid, this is one boric acid molecule we are outlining it. This is having planar structure, and we'll be coming to the explanation why it is going to be planar and why this is forming so many hydrogen bonds. So this slippery nature of the boric acid, we know that is what it has been used in different cases as a lubricant, like we use this in the carom board games. Like you remember those carom games where we were putting some white powder, that was boric acid basically. So that slippery nature of this boric acid is coming from the fact that the structure is actually like the graphite. In graphite, what we used to know, there was one such layer, there was another such layer. So this layer and this layer were bonded by relatively weaker van der Waals forces. So then one layer was sliding past over another layer. That's how the graphite was working as a lubricant. Similar structure is here for the boric acid as well. So boric acid is also having layered structure. So here there are many such boric acid molecules present, like one we are showing over here. There can be another such structure coming at the top of that, and in between them there will be some interlayer separation, which is going to be having the nature of the van der Waals attractive forces. So van der Waals attractive forces may not be very much strong. The layers can slide past very easily because these are bound by hydrogen bonds. Hydrogen bonds are going to be relatively stronger attractive forces, right? So that is how slippery nature of the boric acid is coming. Now we are going into explanation why there are going to be these different number of 6 hydrogen bonds per boric acid molecule. So see here, every hydrogen, this is hydrogen atom and this is oxygen atom. Every hydrogen atom will be connected to the next oxygen of the boric acid. So this hydrogen is bonded to the oxygen of the very next boric acid molecule. First thing. So because one boric acid is having 3 hydrogen atoms, 3 hydrogen bonds are coming from the 3 hydrogens in one boric acid. Then every oxygen is also forming the hydrogen bond. So this oxygen is, let us say, present. This oxygen, it is forming hydrogen bond with the hydrogen of the next boric acid molecule. Now why this only one hydrogen bond? Because oxygen is having two lone pairs in boric acid, right? We have seen structure of boric acid, like this is the thing. There may be other two such ways. So why only one lone pair is forming the hydrogen bond? Why not the another lone pair? Because in the water molecule we have learned that water was forming 4 hydrogen bonds, each from hydrogen and each from the lone pair. The reason over here is because in boric acid, we want to keep our molecule, this molecule is found to be flat. So if it is going to be flat, one lone pair, let us say we are saying in this oxygen molecule, the one lone pair is present in this orbital, which orbital is coinciding with the empty orbital of this boron. There is no electron present, so there can be back bonding happening. The only other lone pair of this boron which was present in the same plane, this was forming hydrogen bond with the another hydrogen. So because oxygen in boric acid is going to be sp2 hybridized, one lone pair remains in the plane, another lone pair becomes perpendicular to the plane. That sp2 hybridization of oxygen is explaining everything about the structure of the boric acid. So one boric acid forms 6 hydrogen bond, 3 coming from hydrogen, 3 coming from oxygen, and this is because of the sp2 hybridization and planar structure of the molecule. I hope that's very much clear. Moving to the next option, option number 4. This was a question about diborane, very much familiar molecule. We have seen about this already. That's the structure of diborane. They say how many atoms are going to be present in the same plane. You can draw your plane in different possible ways. What we have done, we have shown the terminal BH2 groups to be in the plane of the benzene ring. In the plane of this diborane molecule, and the 2 hydrogen which were bridging we have shown to be going below and out of the plane. And we understand here, because every boron is an sp3 hybridization, we know that in sp3 hybridization 2 bonds we can keep in the plane and 2 we can keep out of the plane. So we chose the terminal hydrogen bonds to be present in the plane and the bridging hydrogen bonds to be present out of the plane. And in out of the plane, one goes below and one goes above. So for this boron, the 2 right hand side hydrogens are in the plane, the left 2, the bridging hydrogen, are out of the plane, and on the left hand side for this boron again 2 terminal hydrogens are going to be in the plane and the bridging hydrogen out of the plane. So our plane of the screen, that is what we have shown, it is going to have all the hydrogens in this plane. So these 6 atoms are going to be 6 atoms in total, out of which 4 hydrogen and 2 borons, they are going to be in the same plane. That was our question about this inorganic chemistry, the boron, hydrogen and diborane things. Out of the 4 options given, we could see option A, C, D was correct. That's all for now. Thank you. Bye-bye. Stay tuned. Stay connected for more such questions, more such informations. Thank you. Bye-bye. Take care.